Let's take a look at some familiar objects. When I move among these objects, there is no change in the position of these objects. That's because these objects are at rest. Now let's see what happens when these objects move. Wow! Did you see how fast the car zoomed away? The ball has also disappeared out of sight. The globe shows how the Earth rotates on its axis. But the rocking chair is still here. Its movement looks very inviting. I'd like to relax in this chair. So, what changed around me? The objects that were at rest started moving or were in motion. Motion can be of various types. It can be regular and controlled, like in a watch, or erratic and uncontrolled, like that displayed by the tsunami that took thousands of lives. Now, how far do you think the car will go? How long will the globe take to rotate completely on its axis? You can obtain answers to such questions through the study of motion in physics. These answers will help you control motion and harness it for constructive purposes, like in a hydroelectric dam.
In this lesson, you will learn about motion and related quantities. At the end of this lesson, you will be able to define motion, identify instances of motion encountered in our everyday life, analyze motion along a straight line, identify uniform and non-uniform motion, calculate speed and average speed, define velocity, calculate velocity of a moving object, explain scalar and vector quantities, define acceleration and calculate acceleration of a moving object. In everyday life, you see some objects at rest and others in motion. Birds fly, horses gallop, water flows through rivers, and cars move. You say these are in motion. Thus, motion is a state of an object in which there is a change in its position with respect to its surroundings and time. When a car race starts, the position of each car participating in the race changes relative to the stands, spectators, and so on. This is because the cars are in a state of motion. Tiny particles such as atoms and molecules and heavenly bodies such as planets, stars, and galaxies are all in motion. For example, Earth rotates around its own axis and revolves around the Sun in an orbit. Similarly, other planets, solar systems, and galaxies in the universe are all constantly in motion. None of the moving objects that we have looked at exist in isolation. They may have other moving or stationary objects in their environment. What happens when we compare the state of two or more than two objects? For instance, let us consider the state of a car driver. Is he at rest or in motion? It is difficult to answer this question. This is because, with respect to the car, the driver is at rest. But with respect to the other things around, he is in motion. Thus, the states of rest and motion of bodies are relative. Absolute states of rest or motion do not exist. Consider a bus moving along a road. A passenger in the bus perceives the trees and other objects outside the bus to be moving, while his co-passengers seem to be at rest. Similarly, we cannot see the rotation or evolution of the Earth. However, based on the changes in the environment at various times of the day and transition of seasons, we can infer that the Earth is rotating on its axis as well as revolving around the Sun. Hence, overall, you are in motion as a part of Earth, but at the same time, you are at rest with respect to your immediate surroundings. Motion of objects or bodies can be one-dimensional or linear, two-dimensional, or three-dimensional. One-dimensional or linear motion involves an object moving along a straight line or in a specified direction. For example, cars moving along a straight path in the circuit exhibit linear motion. In two-dimensional motion, in a given plane, an object moves in two directions at the same time. For example, a golf ball, when hit, flies off making a large parabolic path over the golf course. It travels in two dimensions or directions at the same time, horizontal and vertical. If we observe an airplane taking off from a runway, it ascends rapidly in one direction and after gaining some height, turns towards its flight path. This type of motion, where an object moves in three directions at the same time, is called three-dimensional motion. In this lesson, we will cover motion along a linear path in detail. You can measure the magnitude of movement of an object using two quantities, distance and displacement.
Hi, I am called displacement. I will always show you the shortest distance between the initial and final points, or the aerial distance between 2 points. My cousin is called distance. We often look similar, so it can be a little confusing for people at times. However, there is a unique feature that sets me apart from my cousin: my sense of direction. In fact, because of this characteristic, I always display a special bold letter or an arrow on my head.
Let's look at these quantities using an example. At the end of her school day, Mary goes from the school to the playground. The school is 3 kilometers away from her home and the playground is 4 kilometers away from the school. So, from home to school to the playground, Mary travels a total of 7 kilometers. This is the distance travelled by Mary. Thus, distance is the actual length of the path covered by a moving object irrespective of the direction of motion. However, the straight route from Mary's home to the playground is only about 5 kilometers long. Therefore, Mary's displacement from home to the playground is 5 kilometers, as against the distance covered by Mary in reaching the playground, which was 7 kilometers. Thus, displacement is the shortest distance between 2 points irrespective of the path between the points. When an object is in motion, its motion may or may not be consistent all through its journey until it comes to rest again. Let us observe the yellow car in the race. What do we see? The car moves 50 meters every second continuously. Thus, for each second, if we note down how far the car has moved from the starting line, we see that the displacement during any 2 consecutive seconds is the same. This car is in uniform motion. An object is said to be in uniform motion if it shows equal displacements in equal intervals of time, however small these intervals may be. Now let us observe the red car in the race and record how far it has moved from the starting line for each second of motion. We see that its displacement during any 2 consecutive seconds is not the same. This is non-uniform motion. An object is said to be in non-uniform motion if it travels unequal distances in equal intervals of time, or equal distances in unequal intervals of time. Different objects may take different amounts of time to cover a given distance. How fast does a moving object change its position? The answer to this question relates motion to the time taken for the change of position, and that brings us to speed. Speed of an object is the rate at which an object covers a given distance or changes its position. Speed is calculated as a ratio of distance covered to the time taken to cover that distance. Thus, an object that covers a relatively large distance in a short amount of time is moving at a high speed. Conversely, a slow-moving object has a low speed and covers a relatively small amount of distance in a relatively longer duration. An object at rest has no speed. Speed is measured in centimeters per second in the CBSE system and as meters per second in the SI system. Typically, you measure speed in kilometers per hour. 1 kilometer per hour equals 5 divided by 18 meters per second. Or 1 meter per second equals 3.6 kilometers per hour. Let's try applying this formula to one of the situations we reviewed earlier. In our previous example, Mary's school is 3 kilometers away from her home and the playground is 4 kilometers away from the school. If Mary walks to school from home in 20 minutes, her speed can be calculated as 3000 divided by 1200, which is 2.5 meters per second or 9 kilometers per hour. However, generally, the motion of an object is not uniform from its starting point to its final destination. Its speed varies at different points or stretches in the journey. In such cases, to determine the speed at which the object covers the total distance, you may need to gather data on the speed of the object at each instant when it is in motion, and then calculate the average of all these instantaneous speeds. However, gathering so much of data can be tedious, and certainly impossible in the case of large distances. Therefore, we typically use a quantity called average speed in our calculations. The average speed of an object is the ratio of the total distance covered by the object to the total time taken by it for covering that distance. Like motion, speed can be uniform or non-uniform. Thus, an object in uniform motion has uniform speed, and an object in non-uniform motion has non-uniform speed. If you rearrange the formula for speed, you can determine the distance covered in a given period of time at a given speed. S is equal to d divided by t. Therefore, d is equal to s multiplied by t. However, it does not give you the displacement of the object. To determine the displacement of an object, you need to know the direction of motion, along with the rate of the motion. Velocity is the speed of an object moving in a definite direction. Velocity of an object is defined as the rate of change in the position of a body. It can also be defined as the rate of displacement of an object. Velocity is calculated as the ratio of displacement of the object to the time interval taken for that displacement. Velocity is measured as centimeter per second in the CBSE system and meter per second in the SI system. Similar to speed, velocity is also measured in kilometers per hour. Velocity of an object can change by either changing its speed in a particular direction or by keeping the speed constant and changing the direction. When the yellow car takes a turn and moves ahead, its velocity becomes variable. Like average speed, you can calculate the average velocity of an object having non-uniform motion. Average velocity is defined as the ratio of the total displacement to the total time taken. When a body is moving with variable velocity for t total time duration, u and v are the magnitudes of its initial and final velocities, during which it has a total displacement, that is, s total. The average velocity of the body is the average of u and v. That is, it is half the sum of initial and final velocities.
Hi, can you make out the change in the velocity of my hands as they work round the clock to tell you the time? The tip of each hand moves with uniform speed but changes direction continuously as it moves in a circular path. Thus, if you consider the second's hand, its velocity actually changes each second. When the second's hand completes one full rotation in 1 minute, it comes back to its original position. At this point, its displacement becomes zero, and hence the average velocity also becomes zero.
So far, we have reviewed some related measures of motion, that is, distance and displacement, and speed and velocity. Among these measures, distance and speed have only magnitude, whereas displacement and velocity have magnitude as well as direction. A physical quantity that has only magnitude but no direction is scalar. Length, area, distance and speed are all scalar quantities. On the other hand, a physical quantity that has both magnitude and direction is vector. A vector such as displacement is simply a scalar with direction. Let's look at a car in the race. A yellow car is currently at a distance of 7 kilometers from the starting line. However, if we measure the straight line from the starting line to the position of the yellow car is positioned at a point just 5 kilometers towards the northeast direction. Here, distance of 7 kilometers is scalar, whereas the displacement of 5 kilometers towards the northeast is a vector. For an object in non-uniform motion, its velocity may change with time. Rate of change of velocity is expressed in terms of acceleration. Thus, if a body moves in such a way that its velocity changes, then it is said to be accelerating. Observe the car moving swiftly in the circuit. When it approaches the turn, it slows down and after negotiating the turn, quickly gains velocity again. This change in velocity of the car is known as its acceleration. Acceleration is the ratio of the difference of final and initial velocity to the time interval during which the velocity has changed. Acceleration is a vector quantity and is measured as centimeter per second square in the CGS system and as meter per second square in the SI system. Like speed and velocity, the acceleration of an object can be uniform or non-uniform. A freely falling body gains velocity due to gravitational forces at a uniform rate. Thus, it shows uniform acceleration. However, a car negotiating a turn shows non-uniform acceleration because its velocity changes at a non-uniform rate. When an object moves such that its final velocity is less than its initial velocity, it is said to possess negative acceleration or retardation. Here, the two buses A and B are moving along a straight path. The bus A is gaining velocity, hence it is accelerating, whereas the bus B is losing velocity, and hence it is retarding. For example, Consider a bus traveling with a velocity of 20 meters per second. The bus comes to a halt at a bus stop over 5 seconds. In this case, the acceleration of the bus is -4 meters per second square. Thus, we say the retardation of the bus is equal to 4 meters per second square. To summarize, let's take another look at the relationships between the quantities we just studied. Distance represents the extent or length of motion. When distance is mentioned with the direction, you get displacement. A change in distance with respect to time gives you speed of motion. Similarly, the rate of change of displacement gives you velocity. When you measure the change in velocity with respect to time, you get acceleration. The section on solved problems provides you an opportunity to review some model problems based on these concepts. To revisit the key points covered in this lesson, please review the flashcard. Remember the hare and tortoise story your granny read to you in your childhood? The story goes like this. A hare was watching the slow progress of a tortoise on a path in the jungle. Being a faster runner himself, he began to make fun of the tortoise. The tortoise challenged the hare to a race, and the hare accepted confidently. When the race began, the hare shot ahead and ran briskly for some time. Then, seeing that he was far ahead of the tortoise, he decided to sit and relax for a while before continuing the race. He soon fell asleep. The tortoise, plodding on, overtook him and finally won the race. The table provided shows the data on their progress during the race. Similarly, the graph represents the same data. Can you see how the hare was making progress? But the hare lagged behind in the end because he stopped at 1.8 kilometers. The tortoise, on the other hand, walked without stopping and made steady progress. Isn't it easy to make out who won the race and how? Graphs help us communicate information visually. They enable us to understand quickly trends that would otherwise need lengthy written descriptions. As you have studied in mathematics, a straight line graph helps in solving a linear equation with two variables. In this lesson, you will learn about graphical representation of motion. At the end of this lesson, you will be able to explain how graphs can be used to represent and solve problems related to motion. Plot various types of distance-time graphs. Calculate the speed of an object at a given instant using the distance-time graph. Plot various types of velocity-time graphs. Calculate displacement using a velocity-time graph. Identify the significance of equations of motion. Derive the equations of motion. And explain the concept of uniform circular motion. Graphs typically contain both an independent and a dependent variable. For example, consider the graph shown. It plots the runs scored by a cricket team in a one-day match. If you observe the cricket match graph, the number of overs bowled in a match is independent of how many runs came off an over or how many wickets were taken. Since the number of overs is an independent quantity, it is taken on x-axis. Similarly, we can use line graphs to describe the motion of an object. In motion graphs too, physical quantities such as distance or velocity show dependence on time, while time is an independent quantity. Therefore, time is always taken on the x-axis and the other physical quantities are taken along the y-axis. You can create graphs in motion by comparing distance, displacement, or velocity to time. By representing the motion of an object graphically, you can Infer the nature of motion. Determine its position at any interval. Calculate its acceleration, displacement, velocity, etc. at any instant. And derive equations of motion. Two of the most commonly used motion graphs are the distance-time graph and the velocity-time graph. A distance-time graph represents the change in the position of an object with time. In such a graph, time is taken along the x-axis and distance is taken along the y-axis. The graph is plotted adopting a convenient scale for the distance and time. For example, you can use a scale of 1:10 on the x-axis for time. A scale of 1:10 means that each unit on the graph represents 10 seconds. Let's see how a distance-time graph is plotted using some sample data. To plot the distance-time graph, we begin with fixing two axes, x and y, on a sheet of graph paper. On the x-axis, we mark the equal time intervals according to a convenient scale. Say 1 unit equals 10 seconds. Again, using a convenient scale on the y-axis, we mark the y-axis at equal intervals. For example, as mentioned earlier, your scale could be 1 unit equals 10 meters. For each set of figures, locate and plot a point at which the perpendiculars drawn from the respective time and distance values on the axis intersect. Finally, we connect all the points, starting from the origin using straight lines. This gives us a distance-time graph for the data provided. Considering the nature of the motion of a body, a distance-time graph may show a body at rest, a body with uniform motion, and a body with non-uniform motion. If a body is at rest and does not move, we say the distance travelled by the body is 0, no matter how much time has elapsed. The distance-time graph for such a body at rest is plotted as a straight line along the x-axis. However, consider a situation where the body has already travelled a distance of 5 meters. When we start analyzing data on its movement, it means that the body is at 5 meters at 0 seconds. If the body continues to be at the same position for the rest of the time, then the graph is a straight line parallel to the x-axis. When a body exhibits uniform motion, it travels equal distances in equal intervals of time. For example, consider a body moving with uniform speed. The data provided represents the position of the body at different instances of time. The initial position of the body is 0. The graph for this body is a straight line, making an angle with the x-axis and passing through the origin. Thus, the graph of a body in uniform motion is an inclined straight line passing through the origin. When a body exhibits non-uniform motion, it travels either unequal distances in equal intervals of time or equal distances in unequal intervals of time. For example, the table gives the position of a body at different instances of time. When we plot the distance-time graph for the data given, we observe that the distance-time graph for a body having non-uniform motion is a curve. Let's analyze this data further. During the first 10 seconds, the distance travelled by the body is 5 meters. Thus, the speed of the body for the first 10 seconds is 0.5 meter per second. For the next 10 seconds, the distance covered by the body is 10 meters. Hence, the speed of the body during the second 10-second interval is 1 meter per second. We observe that the speed of the body increased with time at a constant rate. Hence, we can say that the body moves with uniform acceleration. Thus, for a body with uniformly accelerated motion, the distance time graph is in shape of a parabola. Now let us consider a body moving unequal distances in equal time intervals. As you can see, a graph plotted based on the data provided again shows a curve. Now, let's look at how we can use the distance time graph to make deductions about speed. To determine the speed of an object, consider a segment PQ of the distance time graph of an object in uniform motion. Draw a line parallel to the y-axis from point Q and another line parallel to the x-axis from point P. These parallel lines intersect each other at point R to form a triangle PQR. On the graph, PR denotes the time interval, while QR corresponds to the distance. You can see from the graph that as the object moves in time interval t2 minus t1, the distance it covers is s2 minus s1. By definition, speed is the ratio of distance covered to the time taken in covering that distance. Therefore, the speed of an object v is equal to s2 minus s1 divided by t2 minus t1. Note, you can also use the term uniform velocity in place of uniform speed if the magnitude of displacement equals the distance travelled by the object along the y-axis. Like the distance time graph, the variation in velocity with time for an object moving in a straight line can be represented by a velocity time graph. In a velocity time graph, time is taken on the x-axis while velocity is taken along the y-axis. Using a velocity time graph, you can determine the nature of the motion, the velocity of the body at any instant, displacement of the body as the area under the graph, the instantaneous acceleration, and the equations of motion along a straight line. Let's consider the different cases that can be represented by a velocity time graph. Body at rest. Body with uniform velocity. Body with uniform acceleration. Body with non-uniform acceleration. And body with uniform retardation. The displacement is 0 for a body at rest, and hence the velocity is also 0. A velocity time graph plotted for a body at rest displays a straight line along the x-axis. When a body moves with uniform velocity, there is no change in the velocity with respect to time. Therefore, the velocity time graph for a body with uniform velocity will be a straight line parallel to the x-axis. The point where the line intercepts the y-axis shows the magnitude of the uniform velocity of the body. When a body exhibits uniformly accelerated motion, the velocity time graph represents a straight line passing through the origin and subtending an angle with the x-axis. This is because in this motion, the velocity of the body increases uniformly with time. The velocity time graph for a body moving with non-uniform acceleration is a curve and not a straight line. The velocity time graph for a body moving with uniform retardation is a straight line making an obtuse angle with the x-axis. Just as you can use a distance time graph to determine the speed of an object, you can use a velocity time graph to determine the displacement of an object. The area under a velocity time graph gives you the displacement of the body in a given time. Consider the velocity time graph of a car moving with uniform velocity, say 30 meters per second. To determine the displacement of the car between points A and B, which represent the position of the car at durations 20 seconds and 30 seconds respectively, draw perpendicular lines from A and B to intersect the x-axis at point C and D respectively. The time taken, t, by the car to move from the position represented by point A to the position represented by the point B is the difference of time t2 and t1. We can say AB is equal to CD is equal to t2 minus t1 is equal to 30 minus 20 is equal to 10 seconds. Since the car is moving with a uniform velocity, the magnitude of its velocity is the same at all points on the graph. Velocity v is equal to AC is equal to BD is equal to 30 meters per second. By definition, the velocity of an object is the ratio of displacement to time. Therefore, we can say that displacement is the product of velocity and time taken. Substituting v and t in the expression S is equal to Vt, we get S is equal to AC multiplied by AB. This is nothing but the area enclosed in rectangle ABCD under the velocity time graph. Thus, in this case, the displacement of the car is equal to 30 meters per second multiplied by 10 seconds is equal to 300 meters. Similarly, you can also determine the displacement of a body moving with uniform acceleration. Consider the velocity time graph. To determine the displacement of the body between points A and E, from both points A and E, draw two lines parallel to the y-axis, intersecting the x-axis at points B and C respectively. From point A, draw a line parallel to the x-axis to intersect the line CE at D. The area under the velocity time graph between points A and E is the sum of the areas of the rectangle ABCD and the triangle ADE. Hence, the displacement is equal to S is equal to AB multiplied by BC plus half of AD multiplied by DE. Analyzing a velocity time graph enables you to derive the equations that define the relationship between velocity and acceleration of a body moving in a straight line. These equations are collectively referred to as equations of motion. There are three equations of motion. V is equal to U plus AT. S is equal to UT plus half AT square. 2AS is equal to V square minus U square. These equations are used to determine the position, velocity, and acceleration of an object. We can derive these equations graphically. The first equation of motion is known as the velocity-time relation. Consider a velocity-time graph for a uniformly accelerated moving object as shown. In the graph, u is the initial velocity of the object represented by the point A. V is the final velocity represented by the point B. T is the time in which velocity changes from u to v. From point B, draw two lines BC and BE perpendicular to the x-axis and the y-axis respectively. From point A, draw a line AD parallel to the x-axis to intersect BC at D. Now, OA represents the initial velocity u. BC represents the final velocity v. OC represents the time t. And BD represents the change in velocity in time t. OADC being a rectangle, OC is equal to AD, and hence AD also represents the time t. BC is equal to BD plus DC, which is equal to BD plus OA. Let's call this equation 1. Substituting BC is equal to V and OA is equal to U in equation 1, we get V is equal to BD plus U, or BD is equal to V minus U as equation 2. The acceleration of the object is the ratio of change in velocity to time taken. From the graph, acceleration A is equal to BD divided by AD, which is equal to BD divided by OC. Let's call this equation 3. Substituting OC is equal to T in equation 3, we get A is equal to BD divided by T, or BD is equal to AT as equation 4. Equating equations 2 and 4, we get AT is equal to V minus U. Therefore, V is equal to U plus AT. Let's now derive the second equation of motion, that is position-time relation. In the same velocity-time graph, we used to analyze position-time relation. Let S be the displacement of the object in time t. You can determine the displacement of the object as the area of the trapezium OABC under the curve. The area of OABC is the sum of the areas of rectangle OADC and triangle ABD. Area of a rectangle is product of its length and breadth, while the area of a triangle is half the product of its base and height. Area of OABC is equal to OA multiplied by AD plus half of AD multiplied by BD. Substituting OA is equal to U. AD is equal to OC is equal to T. And BD is equal to AT, which equals S is equal to U multiplied by T plus half of T multiplied by AT. Therefore, S is equal to UT plus half AT square. The third equation of motion, called position-velocity relation, is derived using the first two equations. In the velocity-time graph, the displacement of the object S is also equal to the area of trapezium OABC. Area of trapezium OABC is equal to half of OA plus BC multiplied by OC. Substituting OA is equal to U, BC is equal to V, and OC is equal to T, we get S is equal to half of u plus v multiplied by t as equation 1. Rearranging the velocity-time relation, we get t is equal to v minus u divided by a. Let's call this equation 2. Substituting equation 2 in 1, we get S is equal to v plus u multiplied by v minus u whole divided by 2a. By simplifying this expression, we get the position-velocity relation. That is, 2as is equal to v square minus u square. Consider the movement of the seconds hand in a clock. As the clock ticks, the tip of the hand moves in a circular path, covering equal distances in equal time intervals. In each time interval, the hand subtends the same angle at the center of the clock. Such a motion, when an object moves in a circular path with uniform speed, subtending equal angles at the center of the circle in equal intervals, is called uniform circular motion. Other examples that you can relate to include the rotation of the Moon and the Earth, a satellite in a circular orbit around the Earth, and so on. How would you calculate the velocity or the distance covered during uniform circular motion? Let's analyze the example of an athlete who is running along a circular track. The distance covered by the athlete at the end of one lap is equal to the circumference of the track. S is equal to 2 pi r. The speed of an object is the ratio of displacement to time. Hence, the speed of an object in uniform circular motion is v is equal to 2 pi r divided by t, where r is the radius of the circular track and t is the time taken to circumnavigate the track once. Thus, you can use this formula to determine the speed of an object in a uniform circular motion. This brings us to the end of this lesson on graphical representation of motion. In this lesson, you learned how to use graphs to analyze trends and derive and apply equations of motion. You also learned about uniform circular motion. The section on solved problems provides you an opportunity to review some model problems based on these concepts. To revisit the key points covered in this lesson, please review the flashcard at the end of this lesson.